Hi everyone, my name is JorgeDiaz. I am a PhD student of the Electrical and Computer Engineering department. I work in my research with Professor Sandra Biedron, and I have decided to talk about Clysons and the LCLS for this final project. I will start with the motivation to talk about Clysons and the LCLS. Then I will go into history of Clysons, then a little review of how a Clyson works, um, then the LCLS and the Clyson at LCLS, and some performance and reliability measurements and studies that have been conducted on this type of Clyson. Then a little bit of information about LCLS2, and finally references. The motivation to pick Clysons and the LCLS as the topic for my final project is because I do my research at the LCLS2 with the low-level RF team, and I have seen how the LCLS is the main project that Slack has right now, and it's been there for the last 10 years. Um, Actually, in April 10, we celebrated 10 years of science at the LCLS. Some more facts about LCLS is that it was the first hard X-ray free electron laser. It had only one experimental station at the beginning, and now there are several experimental stations. 200 scientists were involved in the first run, and now more than 1,000 scientists are involved per run. A run is roughly 1 year. 31% of the publications related with the LCLS are published in high impact journals like Science and Nature. So all these facts in science are the ones that motivated me to do my final project in Clysons. And also because the history of Clysons is closely related with Slack, with Stanford, and with Silicon Valley. So starting with the history of Clysons, we have to go back to 1932 when Professor Rosansky proposed a method of producing electron beams. Electron beams are necessary to make a Clyson work. Also, in 1935, Professor Hansen at the physics department at Stanford University invented the microwave resonator. It was a cavity that resonated at 380 megahertz with an unloaded quality factor of 50,000. It was called the Rumbatron, and it was published in the Journal of Applied Physics under the title A Type of Electrical Resonator. So these two researchers developed the basic concepts that allow the invention and the functionality of the Clyson in the next years. In 1937, the Varian brothers, with the help of Hansen, invented the Clyson. It was a project sponsored by the physics department of Stanford with $100 per year for materials and supplies. At the end, it was a good deal for Stanford because they got about 2.5 million in royalties. So here we can see the Stanford Model A Clyson, which was the invention of Varian brothers and Hansen. The motivation for the Varian brothers to develop the Clyson was to get a microwave source for radar and to use it in airplanes to do blind landing. So maybe a kind of landing in foggy conditions. And also it was used for applications in World War II. The $100 idea paper is very interesting and has a really nice facts about the invention of the Chrysler. Then after this, Hansen kept working with clystrons and particle accelerators and electron beams, and developed the first coupled cavity electron accelerator. And here is a picture of Hansen with his students at that point. Then in 1944, the klystron CV150 was invented, and in 1948, the Mark III klystron was invented. It was a huge advance in power, as we can see in this plot. We are jumping from 2 megawatts to 30 megawatts of power, and we can actually see how the size is also scaled in this picture of the little CV klystron versus the Mark III klystron. Since then, a lot of klystrons have been invented. We have the SLC klystron at the SLAC. SLC stands for Linear Collider. In the 80s, then we have the DAISY klystron, which was designed by SLAC, but is used at DAISY, which is a research facility in Germany. This was in the early 90s. And then in the late 90s, we have the SLAC klystron NLC. So a lot of klystrons have been designed after that and have been used in radar, television, and space communications. So now I'm going to recall how a klystron works, as we already saw on the lectures of the class. So main components of the klystron are the cathode that generates the electrons that will be accelerated, the collector, which receives the electrons, microwave input and output couplers to introduce the RF signal and to extract the amplified RF signal. So actually a klystron is an amplifier. The electron beam, Boncher cavity, which is the first one. Then we have gain cavities, and then we have the extraction cavity, which is the last one. And we have the drift tube where the electrons travel. So a klystron basically is a device that takes kinetic energy from electrons and converts that to electromagnetic energy of the RF field, of the extracted RF field. And it works under the principle of accelerating and decelerating electrons depending on the phase of the electric fields in the cavity. So how it works, basically we generate electrons at the cathode. These electrons come up the same speed, but then when they face the first cavity, the Boncher cavity, they are accelerated or decelerated depending on the phase of the electric field. Next cavities, what they do are basically they make these bunches that have been created in the first cavity. They make these bunches even more dense and more defined. Finally, when we get to the last cavity, the kinetic energy of the electrons is transferred to the to electromagnetic fields inside the cavity, and this is because the frequency of the electrons passing through the cavity is the resonance frequency of the cavity. So they are coupled. The beam and the resonance frequency of the cavity are coupled, and that's what allows us to transfer this RF power. And finally, the electrons that doesn't have much power anymore, they crash in the collector. The efficiency of a klystron is usually 30%, more or less. So yeah, 60% of the energy is lost. Now we can talk about the LCLS, which stands for Linear Coherent Light Source. We have here a picture on the right. It has a macropulse repetition rate of 120 Hz. It operates at 2.856 GHz, and the final electron energy is 13.6 GeV. Each cavity of the LCLS has 87 cells. The cells are shown in this picture in the bottom left. These 87 cells altogether are about 10 feet long, so each cavity is 10 feet long, 320 cavities, and since we have one klystron per 4 cavities, we have 80 klystrons in total for the LCLS. The fact that we have multiple cavities per klystron, this architecture is called vector sum configuration. So the main components of LCLS are the injector or electron gun, where electrons are produced, the LINAC, which is the particle accelerator itself, then the undulator, which we saw in class how it works, is a series of magnets alternating north and south pole, and this makes the electron beam to travel to wiggle and traveling in a kind of sinusoidal path, and this makes the electrons to radiate X-rays, and then those X-rays are used for experiments and research at the experimental stations. Also, it's good to mention that the gallery and the tunnel of the LINAC have been used for several experiments, not only for LCLS. So we have SLC, PEP, PEP2, SLB, FACET, SSRL, and LCLS. And in the future, we will have LCLS2 also. So the gallery and the LINAC have been there actually for about 60 years. Here we have a nice diagram of the LCLS with the energies, the energy after the gun, 6 MeV, the energy after the first section of the LINAC, 135 MeV, and so on, till we get to the undulator, where the electrons have an energy of 13.6 GeV. Also, in the plot on the right, we can see the experimental stations, and that's where like all the research the research is done. SLC was a project before LCLS. It used the same klystrons that LCLS is using, but it had 960 cavities for a total of 240 klystrons. Also in a architecture of one klystron per 4 cavities. Now let's talk about the LCLS klystron, which is the SLAC 5045 S-band klystron. The name comes from the original 50 megawatt peak output power and 45 average output power. Right now, LCLS operates at 65 megawatt peak output power and 41 kilowatt average output power. We have another numbers here, like the frequency that I already mentioned. Another interesting number is the gain, 50 dB, and the saturated efficiency of 45%, which means 45% of the energy of the electrons is given to the RF field that then is extracted with a waveguide. And here we have a picture of the klystron with the main components: again, gun, cavities, drift tube, extraction cavity, and collector. So one of the main measurements for reliability and performance of a klystron is the MTBF, which stands for mean time between failures. It is a really important measurement because LCLS wants to deliver high quality beam to the users most of the time. So they need all the klystrons working basically all the time. So that's why this is a really important measurement. Originally, the 5045 klystron was a replacement for the XK5 klystron at the LINAC, and as we can see in this nice plot, the first years of the 5045 klystron were focused on improvement of the design and on achieving that performance in meantime between failures. And so far, after 25 years, 800 tubes have been operated, 800 klystrons have been operated with a mean time between failures of about 100,000 hours, which is a really good number. Now we have some more metrics to characterize the performance and reliability of klystrons. I would say the most important one is the average age of online klystrons, that in 2010, 2011 was about 50,000 hours. Another plot that I really like a lot is the manufacturing yield, which is the percentage of manufactured klystrons that are put into service, and clearly shows like a learning curve on producing klystrons. So at the beginning, in 1983, 1984, they were making a lot of minor changes in the design, kind of by experience, until they get to a point where they really knew how to produce the klystrons, and now they can deliver 70 to 80%. And then we have in this plot the cumulative high voltage runtime, and here the number of klystrons. So we can see that there are some klystrons that achieve 100,000 hours, which is a really good number. And then the average is about 50,000 hours. Then to finish with the LCLS klystron, I have this slide that shows the reasons for klystron failure. So we have this plot in the right. Main reason is related with the window. Then we have vacuum leaks, and then we have low emission, internal gun arcing, and those are the main reasons for failure. It's also good to mention that failure is defined when you have to break vacuum to repair the klystron. Also, klystrons can be repaired 3 to 4 times, and a lot of studies have been done to improve klystron quality and lifetime of klystrons. And one of those studies, they realized that the most common failure, which is the punctured window, has a Gaussian distribution in relation with the high voltage runtime hours of the klystron. So all those numbers and all those studies are really important at the moment of improving klystron, which is happening constantly. The design that is used right now at LCLS it has a lot of variations if we compare with the original design. I just saw this. This is a picture of the klystron gallery. I thought it would be interested. So these are the klystrons here. The waveguide come here at the top. It is split into waveguides. One go to the east, the other one to the west, and they go down in these penetrations that go 30 feet underground to the tunnel to supply RF power for the cavities. So finally, I want to talk a little bit about the LCLS2, which is an upgrade of the first section of the LINAC to superconducting cavities. The superconducting cavities are shown here. They have 9 cells and are made of niobium, which is a superconductive material at 4 Kelvin. On the right, we also have the cryo module, which will have a superconducting cavities. And in this plot, we have an schematic of the LCLS2, with the first section being the superconductive accelerator, and then in the next section is the warm accelerator, which is the old LCLS. Um, just an interesting fact is that for LCLS2, the design doesn't use klystons; it will use solid state amplifiers, and the main reasons for that is cost, because we are using one solid state amplifier per cavity, which is way cheaper than using one klyston per cavity. And also, the SSAs are modular, so they are easier to repair than klystons. So here are the references for my presentation. And thanks for your
Hi
attention.
everyone, my name
Hope
is
you
JorgeDiaz.
enjoyed this
I am a
presentation
PhD
and it was
student at
like
the Electrical and Computer
informative
Engineering Department. I
in
work
some
with
way
Professor
about
Dr. Sandra
klystons and
Biedron,
about their
and I
development
have
and
decided
history
to do
and
my final
performance
project
at
on
LCLS
klystons
at this
and
time.
the LCLS.
Let me know if you have any questions. I'll be happy to answer that. Send me an email and we can discuss further about klystons and LCLS. Thank you so much.